Hello everyone, welcome. For the past couple of videos, we have been trying to build a machine learning model in order to predict the solubilities of organic molecules. So we talked about lots of stuff in the past 6 videos, and in this video, which is gonna be our last video regarding this data science project, so we will be compiling our results and we will try to build a story around these results in a systemic manner, and we will be writing down our results in the form of a manuscript or a project report so that we can communicate our results in a scientific manner. Now, whether you are a graduate student, a master's student, a project student, or just someone who is working on a machine learning project, it is highly important to communicate your results in some form. It could be in the form of an academic publication, or you can publish it on a blog, or it could be a requirement for your curriculum. So basically, you need to know how you can write down your results in an effective and systemic manner. So that is what we will try to achieve in this video. So on here, I am on a table of contents page, and our report would be basically split into 4 or 5 main sections. First one is introduction, then results and discussions, and conclusion. Along with that, we also need to put down the link for our data, so data availability section, and references. Now, one of our most important topic is results and discussion, which has subtopics or subsections. For example, data set and descriptors, data set pre-processing, data analysis, model selection, feature reduction and model evaluation, hyperparameter tuning, predictions, explainability. So we are gonna be talking about all these in this report. So let's just get started with our very first and I think one of the most important aspect of a project report or a manuscript, which is the title. Now, title is often the first thing readers encounter, and a well-crafted title grabs the attention of potential readers, encouraging them to explore the content further. So I'm here giving a very general and simple title for our report, which is a machine learning approach for predicting aqueous solubility of organic molecules. So in this first page, along with the title, you can give in the your name, email ID, date, and all other affiliations that you might have. Moving on to the second page, it also has the title and abstract. Now, abstract of a manuscript is a concise summary of the key aspects of the research presented in the paper. It serves as a standalone piece that provides readers with a quick overview of the study. So here I have talked about predicting solubility, which is the main context of our paper. Then I've talked about the fact that we are going to be using machine learning approach in order to predict the aqueous solubility. I have briefly described about our data set and the steps that we performed in order to reach at our results. We explored random forest and XRT models, and these were the main models that we evaluated. And then we were focused on the interpretability and identified topmost descriptors for building our model. In the end, we did hyperparameter tuning, and we explained the features which we used for building our model. So all that is in here in the abstract, just in a brief manner. So along with that, we have keywords, which is solubility, machine learning, random forest, mod red. You can put in more if you want. Next, we will be moving on to the introduction part. In the introduction, I have talked briefly about what is solubility and why it's important. For example, I've talked about its pharmaceutical relevance. It plays a pivotal role in drug development and formulation, and the ability to predict and enhance solubility is a critical step in optimizing drug formulations and improving patient care. It is also important in environmental science, as it is essential for assessing the potential impact of pollutants, facilitating risk assessment, and guiding remediation strategies. Also, I have talked about the importance of solubilities of organic molecules in material sciences. For example, it plays a key role in the development of coating, adhesives, and other materials. So all that goes in here. Then I have talked about the use of machine learning models for predicting the solubilities. And after that, I have put in some previous studies which were performed using machine learning for predicting the solubility. So I have put in the dataset size, machine learning models which were used. These are mostly multiple linear regression models, their test R2 scores, who developed it, and along with that I have also provided references for these research papers, which is very crucial. Then I have talked about our own research. Here I have put in a figure where I've showcased we have these molecules and their smile strings of 1144 molecules. Then we did feature extraction using Mordred script and extracted 1826 descriptors, and using feature reduction algorithms we truncated the dataset to just few descriptors. After that we built the model using these descriptors and then use that model for predicting the solubilities. And then of course explainability comes into play, because the main theme of our work was interpretability, where we reduce the number of descriptors to just few useful ones. So I have provided that in the form of a figure here. Secondly, this is the most important part where we will be talking about kind of what we did in a coding portion. Like the first part is data set and descriptor. So I have provided in the source from where I got this data set of 1144 molecules. Then if you remember, we use Mordred script for calculating 1826 topological 1D, 2D and 3D descriptors. And here I have talked about a little bit about Mordred, that how it is superior to other established software and the various advantages offered by it. So this last line kind of summarizes the whole section, and it says the expeditious and effective application of Mordred resulted in the generation of 1826 molecular descriptors for the entire set of 1144 organic molecules. Now if we go to the Google Colab notebook, so in here I'm just gonna be talking about some important topics. So let's just start with importing all those libraries which we have used before: Mordred, RDKit, Pandas, NumPy, Seaborn, Matplotlib, and various modules from sklearn. I am setting the background to white grid to give a good look to our graphs, and this is our first section, data set and descriptors. So we had this delane.csv file which had the raw dataset in it. So let me just load this file and show you how it looks like. So we had compound IDs, Meyer log of solubilities, predicted log of solubilities, and smile strings. And what we did was converted these smile strings to molecular objects in here, and then calculated descriptors using Mordred. And then we kind of stored our descriptors along with the compound IDs and Meyer log of solubilities in delane_Mordred.excel file. So I'm not really gonna run these again as it'll take us a long time. So I'm just skipping it for now, and if you're interested you can go and watch these videos, and I have talked at length about how you can generate these molecular descriptors from smiles using Mordred. So I'm just leaving it here. I already have my molecular descriptor data stored in delane_Mordred.excel file. So let me just load this, and I'm gonna be showing you our final data set which we generated using Mordred. So this was our final data set, and it had around 1826 descriptors along with our target. So we can just have a look at our shape. So it has 1826 descriptors. These three are compound IDs, smiles, and Meyer log of solubility. So a total of 1829 columns and 1144 data points. So next we moved on to data pre-processing. Again, you can go ahead and have a look at this video for in-depth detail. I'm just kind of overviewing this section over here. so we had this data set over here. So what we did was we just extracted the features here, and this is just the data has just the features or descriptors in it. And what we did was initially we eliminated all the columns containing erroneous values, so we never had any null values, right? So we got rid of the erroneous or columns containing strings. So what we did was we kind of generated two lists which had the numerical and boolean column names. So let me just quickly go ahead and run this. So the length of column containing just numbers were 1271, and columns containing boolean values were just 2. So 1273 descriptors is what we want at this stage, and we use data slicing to get rid of the other irrelevant descriptors. So this was our data set at this point. Now we went ahead and removed constant values using this code, and we dropped around 153 columns containing constant values, which could be either 0 or 1 or any value. If basically there is no variation in the data in the feature, that's irrelevant to us, right? So that's what we did. We just dropped these columns, and then we removed highly correlated columns, and that's a condition of the regression that there should be no correlated columns, and the threshold for us was 0.80. So if there were two descriptors with Pearson correlation coefficient greater than 0.80, one of them would be eliminated. So that's what we did in these two lines of code. And our new data set, which was new underscore df, had a shape of 281. So, and then if you remember, we had two descriptors which were boolean with true and false values, and we converted these booleans into integers using label encoding, and that's what I did here. And this was kind of our final data set, and all those boolean descriptors were also converted into numerical values. And then we saved this data set in Delane underscore modred underscore truncated.csv file. So that was all about data pre-processing, and that's what I have written down in here. So I mentioned here that initially we had 1826 descriptors, and we got rid of missing and erroneous value, which reduced the number of descriptors to 1273. Further, we eliminated constant values of around 153, and then we had around 1120 descriptors, and in the end we eliminated the highly correlated descriptors, and our threshold was greater than equal to 0.80. And then in the end we converted these two boolean descriptors into binary values of zeros and ones using label encoded, and our final data set had 281 numerical descriptors and 1144 data points. So that was kind of all for data pre-processing. And in data analysis, so in data analysis section, we first had a look at our target, which was measured log of solubilities. So in here, so this is our final data set. So before I move ahead, I'm gonna be changing this name of measured log of solubilities to just log underscore sol, because we are gonna be plotting these in our graph. So this is a kind of big name, so we just want a shorter name for that. So that's what I'm doing here. I'm changing this name to just log underscore sol. And let's have a look at our data set again. So this is our data set, and with 281 descriptors, and these three are just our compound IDs, smiles, and log of solubilities. So let's just analyze our target, which is log of solubilities. So we had some information about it, and what I'm gonna do is I'm gonna add the minimum and maximum, basically range of our target in our report. So our minimum value is minus 11.6 and maximum is 1.58. So our minimum value is minus 11.6, and we wanna know for what compound has the solubility or log of solubility value of 11.6. So what I'm doing is I'm calling a argmin function on our target. So this will provide us the index position at which we have this compound. So let's just grab this index here. So this is the compound for which we have the minimum solubility value, and this is the smile string. Now smile string is not really gonna tell us much, so I'm gonna be converting this into molecular object, and we are gonna be visualizing this using draw.mol to image. So this is our compound for which we have the minimum solubility, and as you can see here, this is highly lipophilic with all these benzene and aromatic rings and all these chloro groups. And we also want to do the same for the maximum solubility. So I'm grabbing the index position 361 where we have the compound with maximum solubility, and I am converting this smile string to an object. So acetamide has the maximum solubility value, and I'm gonna be putting all this information in our manuscript. So next what I'm doing here is I'm plotting a distribution plot. So first I am plotting a figure, and then I'm using SNS to plot a distribution plot of our log underscore solubilities, and these are just the labeling here. So this is the distribution plot of log of solubilities, and although it has a pretty good normal distribution, but it is little skewed towards the right side. So so there is some asymmetry in here, and we will be talking about that in our report. So this was all about target, and next we uh, like I said before in my videos, that we cannot analyze all these 281 descriptor, but we can do for some. And for that, what I'm doing is I'm just extracting the most correlated descriptors. So the descriptor which are most correlated with our target, which is Mayer log of solubilities. And what I'm doing here is that I'm calculating the Pearson correlation coefficient of all the descriptors with log of solubilities, and I'm sorting these values basically in the decreasing order. And I'm just grabbing the first five or first four descriptors here. So let me just run this code and show you. So let me just find the first correlation using this code. Okay, so these are the four descriptors which are highly correlated with our log solubilities. So filter it log S has Pearson correlation coefficient or R value of 0.86. PEOE underscore VSA6 has 0.70 R, and CG has 0.62, and ABC has 0.58. So these are the only four descriptors which we are going to be talking about in the report. And what I have done here is that I have just plotted a bar plot of all these descriptors just to see which is most correlated. This is just for our own analysis. You can, or you can put it in the paper, or you can just leave it out. It's totally up to you. But the main important thing that we do wanna mention, or we do wanna report in the report, is their scatter plots. So in this line of code, what I've done is I've plotted the scatter plots of all these four descriptors with the log of solubilities. So this one is of the filter it log S versus solubility. So on the x-axis we have Mayer log of solubilities. This one is with our second descriptor, this one is with our third, and this is with our fourth descriptor ABC. And from the scatter plot we can get an idea about the correlation. For example, filter it log S and RN CG are positively correlated with our log of solubilities, whereas PEOE and ABC are negatively correlated with our descriptors. So basically, with increase in the value of these two descriptors, we will see decrease in solubilities, and in these two descriptors with their increase, we will see increase in the solubility. So that's the information that we are getting from these scatter plots. And in the end, I also wanna plot a correlation matrix. So what I have done is I've calculated the Pearson correlation coefficient of just these four descriptors with the log of solubilities. So this is the correlation matrix, and we can just plot this in the form of a matrix here. So this is the matrix, and that we are gonna be putting in our paper. So as you can see on this is just the half triangle, and if you wanna just have a look at the log of solubilities and its relationship with other descriptor, you can just focus on these four boxes here. This is the highly correlated and followed by this, and then RNCG, and then ABC. And you can also analyze their correlation with each other. For example, PEOE is only 29% correlated with ABC, and I think the maximum is gonna be 0.80 among us these, because if you remember, we eliminated all the descriptors which were highly correlated. So yeah, that was it for the data analysis section. And in here, that's what I have put in all the information regarding its range from -11.6 to 1.58, and I have also put in the names. The mean value is -3.06, which is slightly lower than the median. So basically we have skewness suggesting an asymmetry in the distribution. And then I have talked about these four descriptors that we identified using correlation coefficient, and these are the figures here. So this is the distribution plot, this is the correlation matrix, and these four are the scatter plots, and I have put in little information about these in the figure title. Now moving on, the next topic is model selection. So for model selection, if you remember from last time, we used lazy predict in order to screen different models, but we are not really gonna be using lazy predict in our manuscript. And let me just run this first, and then I'll tell you why we can't really use this method for model screening. So let's just install and import lazy regressor, and then I'm gonna be defining our y and x variable, which I have scaled over here. And then we will train test split, and then just run our lazy regressor. So it has finished running the code, and here is the result. As you can see here, it is showing Bayesian Ridge as the most efficient model, and with test R2 score of 0.91, followed by elastic net, and extra tree is also good with 0.91, and so on. Now the problem here is that these results are based on just one of train test split. If you change your training and test sets, let's say I'm putting here a random state of 2, and if you just run this again, here you can see that with a different train test split, we have got an extra regressor as our extra trace regressor as our best model, with a value of, or R squared test value of 0.90, followed by his gradient boosting regressor, then lasso CV, and so on. So that's the reason we cannot reach at a decision based on one of test R2 scores. So what we can do is we can cross validate. So let me just screen model using cross validation. So what I'm doing here is that I'm just defining my x and y variables again. You don't need to, we have already done that. So this is our kind of scale data set here with 281 descriptors. So I'm just splitting with the same random state of 45. And what I'm doing over here is that I'm running a for loop in order to get the cross validation score of these four models. Now we know random forest and extra tree work very well, so that's definitely gonna be in our list. I'm using linear regression as well just to see how linear models perform, and SVR is a cluster based technique. So I have kind of mixed and matched different types of models. Now you can put in more models as we want, but since this is just a tutorial, I'm just showcasing you that you can just use different types of models. And again, it's not that lazy regressor is useless. It has provided us information about our some of the good models, like extra tree regressor was kind of consistently performing well, so was random forest regressor. So you are going to be putting these models in our list here, which we are going to be screening. So what I've done here is that I'm running a for loop. Here in the first iteration, it will grab this linear regression class and it will create an instance of this class and then fit our training data, and then we'll use this cross underscore val underscore score method, which would take in argument as our estimator, which in first case would be linear regression, then training set, and our R2 is our scoring method, and we want to cross validate 5 times here. Now in the end, we are going to be printing out the mean of these 5 results here. So let's just run this and let's have a look at our results once it's done. So it has finished running the code, and we have the cross validation R2 scores for each of these models. And if you're interested to know more about cross validation, I have talked at length about cross validation in my previous videos, so you can go check those out. So we have the results here. Now linear regression has a cross validation score in negative. SVR is pretty good, 0.838, and forest is pretty good, and so is extra tree. Now just in case if you are wondering how come we got this minus 8.8 cross validation score for linear regression, so what I'm doing here is that I'm gonna show you. I'm just running again cross validation for linear regression, and I'm gonna be showing you each and every cross validation score. So these are the 5 cross validation scores here. Now this first one is 0.88, which is pretty good. Second one is 0.83, that's also good. Third one is 0.80, great. The fourth one here is minus 4.4 into 10 raised per 24. So that is the problem here. So that's what I was talking about with lazy regressor. Like, we cannot conclude our results just based on one train test split. We need to cross validate 5 times just to make sure that our model is good enough. So here we have a problem, and that is kind of the mean of all these 5 are giving us this minus 8.8. So definitely we are going to be discarding this linear regression. And since random forest and extra tree are pretty good, so what we are gonna do is we are gonna be sticking to these 2 models. But just for the report, we also wanna, along with cross validation, we also wanna run and see our train and test scores. So that's what I have done here, and let's just go to the report. So in here, so that is what I have talked about in model selection. First I have talked about train test splits. So we have allocated 80% to training and 20% to test data, and it was a random split. And model metric was R square, and then we did a comparative analysis of various linear and non-linear multiple linear regression models like linear regression, sport vector machines, random forest, and extra t, which was conducted through cross validation. And I have talked a little bit about what is cross validation, and I have put in that we did 5-fold cross validation. And here I have talked about our results which we have seen before, and I want to bring your attention to this table, which is highly important. I've kind of compiled our results in this table, where this is the result for multiple linear regression, and the cross validate score is -8. Then we have training score and test score, which is quite low, right? So we are not gonna be moving ahead. SVM was better than multiple linear regression model with quite good cross validation, train and test scores. But of course, random forest and extra t kind of stood out with the highest cross validation, train as well as test scores. Now For future studies, I'm gonna be sticking with random forest model. The main reason is that extra t models are more prone to overfitting. As you can see here, the training score is 1, so it has a lot of overfitting, and test is 0.89, and sometimes it can get difficult to decrease overfitting in extra t even with the hyperparameter tuning. So that is why I am sticking to this random forest model, but you can go ahead and use extra tree if you want, and you can further evaluate your model and do hyperparametric tuning on extra t. But for now, for this particular project, I am just sticking with random forest model. So next topic would be feature reduction and model evaluation on a reduced number of features. So what I'm gonna do here is that this is the random forest model. So let's just run this again here. So in here I have put in a random state of 0 just for the reproducibility, and these are the kind of results that we are getting from train and test, and it's quite similar to what we have seen before. Now we are going to be using random forest to do the feature importance, and all we need is this feature underscore importances underscore attribute on random forest estimator, and then we are going to be just plotting our top 8 descriptors. Now, so again, these are the same descriptors that we saw in our previous video: filter it, logas, Lipinski, SIC0, and all these descriptors. Okay, at this point, we have identified these topmost descriptors in a quantitative manner, right? But we don't really know how many descriptors are useful for our model. It could be 2, it could be 3, it could be 4, it could be 10, it could be 15. So so machine learning is like I told before, it's a game of trade-off. Basically, with reduced number of descriptor, you might see a little less predictive power, but at the same time you are making the model interpretable and white box rather than a black box, and that's what we are interested in. So let me just show you the scale as well. So these are the top 8 descriptors with their importance. So 69% contribution from filter it logas, from Lipinski 8%, SIC0 3%, RNCG 2%, RPCG 1%, and so on. Now I'm gonna be slicing our data set based on these 8 descriptors. So this is gonna be our data set df underscore final underscore 8, which would have these 8 descriptor, and I'm concatenating it with our log of solubility. So let's just have a look at our final data set here. So this is kind of the 8 descriptors that we identified, the topmost descriptor, and this is our target. Now in order to see the optimal number of descriptors which we need in our model, what I'm gonna do is I'm gonna sequentially add each descriptor to our data set, and we are gonna be seeing the are 2 values. So basically what I've done here is, let me just print out the names of the columns. So these are the descriptors, right? So what I'm gonna do here is I am defining my target, and then I'm creating an empty list called scores, and then I'm gonna be running a for loop, and in the first loop it will just grab this filter it log as a descriptor, and it will scale it, and it will train test split it, and then it will be fitted into our random forest regressor model, and then we are going to be seeing our train and test results just on this filter it log as. And in the second loop it will grab both of these descriptors. In the third iteration it will grab these 3. In the fourth iteration it will grab these 4, and so on. So we'll have 8 iterations. So let me just run this code, and I will show you the final scores here. So these are the scores here. These are for the train, and this is for the test set. And the first kind of row, or you can say first list, is for the first descriptor. This is for 2 descriptors. This is for 3, 4, 5, 6, 7, and 8. Right. So just to visualize it better, I'm gonna be converting this into a data frame, and let's just have a look at our data frame. So this is basically the screening result here. This is training result, this is test result, and these are the number of descriptors. And as you can see, although there is not much difference in the train scores, but test score is incrementing with each addition in the descriptor, and it's maximum at this point with 7 number of descriptor. And when we added the 8th one, we saw a decrease in the test R2 values. Now let's just plot all this in a graph. So what I've done here is that I've just created a figure, and I have plotted a subplot with this figure size, and then y1 is our train results and y2 is our test results, and then I'm just plotting a line plot with these two lines of codes. And in the first plot I'm just plotting our train, and in the second I'm plotting our test R2 score, and all this is for adding text to the plots, and this is for labeling. On the x-axis we have number of descriptors, on the y-axis we have r square, and I am saving this figure. So this is kind of our final figure, and this is the from the legend you can see this is the training score and this is the test score, and these are the number of descriptor. So these two values basically correspond to just when we have just our first descriptor, filter it log as. This is with combination of 2, 3, 4 and 5 and 8. So so we can put this in our manuscript here, and as you can see here, it is peaking out at this point here where we have 7 number of descriptor. So so basically 7 is our optimal number of descriptor, and that's what we are gonna be using it in our future studies. And we are gonna be eliminating our 8th descriptor. So what we need here is that we need to grab these columns here. So I am kind of slicing this our final data set. So what I'm doing here is that I am combining compound IDs, smiles, log of solubilities, and all the 7 descriptors from this data set here, and I'm generating a final data set with our target as well, and I'm naming it Delane underscore 7 underscore desk. So let's create this data set and have a look at our kind of final data set. So this is our final data set which we gonna be using for our modeling. So it has names, smiles, these 7 descriptors. I have got rid of the last one here, and this is our log of solubilities, which is our target. And you do wanna save this as a CSV file. So that's what I've done here, and now it's time to make a final model. So I am splitting our data into train and test set, and I have not segregated the x and y values yet because we are gonna be needing this data set in our final evaluation, and I'll be talking about that in a minute. So this is our training, and in here I am splitting it into train and test set. So basically these 7 descriptor would be our x train and this would be our y train. And if we look at our test in here, these 7 descriptors would be our y or x test, and this would be our y test. So that's what I'm doing here. I'm just grabbing the columns for our x train, y train and x test and y test from these train and test sets. So let's go ahead and do that, and we just want to make sure we have the right data set. So yeah, x train is 1, 2, 3, 4, 5, 6 and 7 descriptors. So let's just get the scores, and we are going to be putting this in a tabular format for both random forest and extra tree. So these are the scores, cross validation, train and tests for both random forest and extra tree. And I have put all this information in our feature reduction and model evaluation section. So here I have talked about we had 281 descriptors, and then we did a feature importance algorithm, and we identified these 8 descriptors here, and then we sequentially added each descriptor to our model and noted down there are two values, and we plotted this in the form of a graph, and from in here we can see that 7 is the optimal number of descriptors, and I have put all this information in here. And in the end we have screened our random forest and XRT model, and I think this is pretty awesome here. As you can see here, with 281 descriptor, if you analyze our results compared to the one with 7 descriptor, the cross validation, the train and the test scores are pretty similar for random forest model. And for XRT, if we compare, cross validation score is similar, so is the train score, but just the test score has come down a little bit. Now there is one point I want to make here. The reason it has come down is because we have used a random forest feature importance algorithm. Basically we have used feature underscore importance underscore attribute on random forest estimator, not on extra tree. I think if you use this attribute on extra tree regressor, you will end up with different set of descriptors, right? So you might, if you use those descriptors, and you might be able to see the test R2 value closer to this, so you can go ahead and try on your own. So what I'm talking about here is that in here where we use the So in here we have used feature importance attribute on random forest estimator, not on extra tree. So you can go ahead and see what happens with extra tree, but make sure you first create an instance of the extra tree class, and that is it. Then all you need is replace this random forest with extra tree instance, and you will get I'm hoping you will get at least some of the descriptors which are different from what we are seeing now, and you can use those for building your final XRT model. So that's a kind of homework that you can do on your own. In here I am just sticking to the random forest model here. So yeah, that was all about the uh, feature reduction and model evaluation. Now the next step would be hyperparameter tuning, and in here again if you want to have a deep knowledge, you can go visit this video link here, and here I have talked at length about how you can tune your hyperparameters. So I'm just briefly go through this grid search CV which I've used here. So I'm importing this grid search CV class from sklearn.model selection. These are the default parameters that we have for random forest regressor, and these are the parameters that I'm going to be screening using grid search CV, and these are their values. So we are going to be putting all that information in our project report. So we are going to be using grid search CV and create an instance of it, and then we are going to be fitting our training data on this, and then we can just grab the best parameters using best underscore params underscore attribute on this CLF underscore RF. Now since this takes a long time, I'm not gonna run it again, but I have already done it before, and these are the parameters and their values which I have identified using this grid search CV. So I'm just gonna run this piece of code here with the best values for our parameters, and as you can see here, our training score has come down, and that's a good thing that we are really seeing a decrease in overfitting, and our test score has come a little bit down from like 0.865 to around 0.853. So that's what I have put in here. I have talked about hyperparameter tuning and grid search CV, how you can use it to systemically explore a predefined hyperparameter grid, and I have put in information about all these parameters here and their value screened and the final value that we have got, and I have also put in the results that we have got from this. So initially we had a training R2 score of 0.983 which decreased to 0.962, and we just saw marginal decline in the test R2 score from 0.865 to 0.854. So the next section is our predictions. Now this is our final model here with these scores here. So what we are going to use is we are going to be using this random forest model in order to predict our uh, test set values. So uh, all we need is dot predict method, and what I'm doing is I'm plotting a scatter plot. So let me just run this, and I'm going to be showing you the results. So this is kind of the regression plot. So in the first line of code here, I'm plotting a scatter plot between measured and predicted test values. So y underscore test is our measured log of solubilities, and rf dot predict on this x underscore test will give us y pred basically for the test set, and that's what we have plotted it in here. And then I'm also plotting this regression line using sns.reg plot, where x is our y train and y is our predicted y values for our training data, and I've given a color of maroon. This is for transparency, and I've also labeled this as train and this one as test. X label is measured solubilities and y is predicted solubilities here. Now the second plot is that of residue. So let's just first run this, and in here we have on the x-axis we have measured log of solubilities, and on the y-axis we have residue. Residue is basically predicted minus actual values. So error is plotted on the y-axis. So what I have done here is that I have kind of defined y pred y underscore pred underscore train. So that would be our predicted training data, and y underscore pred underscore test would be our predictions for the test data. So in the scatter plot, I have plotted both the test and train values on the x-axis, and on the y-axis we have residue. So y test minus y underscore pred underscore test, and the test values have been given the same color blue, and the train values have been given the color of maroon here. So yeah, that was all about this plot, and it will give you an idea about your errors. Now the points or the molecules which are closer to zero, they are predicted with high accuracy, whereas points like this one over here, they have the maximum error. And in fact we want to see what those molecules are, and that's what we are going to be talking about next. Now before that, just since I want both of these plots in one figure, so I am just running this line of code here. Here I have got both of these plots in single row. So it's just simple. I have used a plot dot figure, and I've created a figure size of 12 by 5, and it's the same thing what I've used before. And then I've just plotted subplots at index position 1 and at index position 2. So yeah, and we can save this using plot plt.savefig, and you can name it. You can give the dpi, you can give 200, 300, 400. b box inches is tied. Basically sometimes what happens is these labels are cut off, so if you use this it will be a complete figure and there will be no overlapping while saving. So yeah, so now next we wanna see our predictions. So basically, so this was our test set with compound ID, smiles, and all the 7 descriptors, and our measure log of solubilities. Now what I'm gonna do first is I'm gonna reset this index here first, and then I'm gonna be concatenating our predicted values here. So our predicted values is in y underscore pred underscore test. So that's what I'm doing here, concatenating it to here, and I'm giving the name as test underscore predictions. So let's have a look at our data set here. So along with our measured log of solubilities or experimental or observed, we have the test values. So as you can see, these are pretty close here. Now this has a high error of around just little less than 2. These are close as well. These are very close. So what I want to do is I wanna first have another column with the absolute error, right? So what I've done here is what we can do is subtract this from this and get the absolute value. So that's what I'm doing here, and I'm generating another column called apps underscore res, and I'm gonna be sorting this value in the decreasing order. So let's just have a look at our data set again. Okay, so along with our measured solubilities test values, we have the absolute error, and these are sorted values. So top five are the molecules with the highest error. And what we need is we need to visualize this as well. I want to see this molecular structure of these molecules here with the highest error, and of course the one with the lowest error. So what I'm doing is I'm just converting these smiles into molecular objects using pandas tools dot add molecule column to frame. So again, have a look at our data set. So it has generated a molecular object column. Now let's just visualize this using draw.moles to grid image. And these are the molecules with the highest error here, and this is the one with the maximum error of 2.81, and these are the absolute errors. This could be positive or negative. This is the one with the absolute error of 2.45, 2.38, 2.24, and this is the one with 2. And if you want to have a look at the molecule with the minimum error, so these are the molecules with minimum error. These thiophenol can be predicted with high accuracy, and there is zero absolute error, and all these are kind of close to zero. So let's just go to our manuscript, and I'm gonna be showing you what I've written here. So I've talked about these thiophenol, pinacolon, and fenfuran. So these are just the R graphs that we have generated, right? This is the regression plot, and this is the residual one. And in here I have drawn the molecules with the maximum error and with the minimum error. So this is kind of a scale with increasing absolute error. This one over thiophenol had zero error. This is pinacolon, and this one here is fenfuran here, and these were predicted with high accuracy, and these are the ones with most errors. So I've talked about them. Now we also need to talk about the reason why we might have seen this high error in these molecules. So what I've written here is that molecules with complex structures or unique features such as the one discussed above are more challenging for the random forest model to accurately predict, probably because the training data does not cover similar structures well, and the model may struggle to generalize to such cases. So it's possible that these molecules which are giving us high error do not have many similar molecules in the training data, as a result of which their prediction is little off our scale. And the other reason could be that the random forest model is slightly overfitting the training data. Therefore, the possibility of performing poorly on some molecule cannot be. So we saw that our model was a little overfit, and that could be the reason for poor performance on these molecules. And the next section is explainability. So in here I've talked about the disadvantages associated with black box models. So scientists who prioritize results that align with their cognitive abilities and knowledge gained from experimentation are hesitant to adopt black box model for the real world application due to their ambiguous nature. So consequently we have built a kind of interpretable model, right? So we just isolated 7 most important descriptor, and fortunately we saw good accuracies with them. And I've talked about all these 7 descriptors in kind of detail in this section. And again, I'm not gonna go into detail, but here is the video where I have talked about how and why these 7 or these descriptors made it to the top of our list. And so I highly recommend you to go and watch this video if you want to get more information, or you can just read this section over here. So I've just talked about filter it log as, which is the computed log of solubilities, and it has emerged as the most vital quantitative descriptor in contribution to the development of random forest model. uh, Now second one is Lipinski, which is nothing but the measure of molecular mass, hydrogen bond acceptor vulnerabilities, octanol water partition coefficient, which is nothing but a measure of solubility. So SICO is a structure information content. RNCG and RPCG take into account relative negative and positive charges, and these two descriptors have minor contribution and represent the spatial arrangement of atoms and molecular properties in a molecule. And I have already given a table here which has the feature labels. So these are the labels of the descriptors. These are little description that I've got from the Moderate website, and this is the feature importance values for all these descriptors here. So this is quite informative, and in the end it's just conclusion. Again, there is a lot you can do, but we already have around 20 pages and a little around 4,000 words. So I'm gonna be ending with conclusion here. Basically conclusion is just about like we have used machine learning model to predict solubilities, and it's highly important, and how we have used these two as our main models, and these are the 7 descriptors that we have used for building our model, so just to make the model more interpretable. So, and in the end we wanna definitely give the link for our code here. So I am providing you the link here, and of course you don't want to miss out the references here. So I have put in around 24 references, so you make sure you put in all the references uh, indicating from where you have got all this information. So I think that is pretty much it. I'm gonna be providing you this on the GitHub repository along with all the code and datas. So make sure you check that out, and uh, that is it for this project here, and I will see you in the next video. Thank you for watching.